This presentation considers a few common everyday subjects of economics and finance. It involves historical time series analyses of the quantities or metrics of interest as shown. What's in a name? That which we call a recession, by any other name, would spell just as worrisome. To be a recession, or not to be a recession? That is the question. The evidence of a recession risk is the negative GDP growth. The evidence of no recession risk is the low employment rates. This presentation provides a quantitative analysis of these two metrics, GDP and unemployment rate, in relation to recession. Are we in a recession or not? It is not just a matter of political talking points. It is an important topic in the world of economics and finance. To an investor, is the market finally in the clear for smooth sailing? Or, will there be an earthquake ahead? Back to what's in a name. In the US, the organization that officially calls the shot on the status of the economy is the National Bureau of Economic Research. This chart shows episodes of economic recession in the US, as determined by NBER, from 1854 to 2022. The latest recession in 2020, associated with COVID-19 pandemic, was the second shortest in the series. It lasted only 2 months. The first recession of significant duration on the chart was the post-Civil War recession. Then came the longest depression in the U.S. history since the mid-19th century, triggered by the collapse of the railroad industry, leading to the 1873 financial panic and the stock market crash, starting an episode historically known as the Long Depression that lasted 5.5 years. In retrospect, the Long Depression marked a growing pain associated with a great epoch of the U.S. economy, the 19th century expansion and industrialization of America. A milestone of this episode was the celebrated completion of the Transcontinental Railroad. This industrial achievement, along with economic growth and prosperity, in a way, represents the pinnacle of the first industrial revolution, taken place in the New World, enabled by the Old World invention of the steam engine a century earlier. Then came the malaise of the late 19th century U.S. economy, also known as the Gilded Age. After a few years of growth and prosperity, inexorably came a downturn, the third longest depression, known as the Depression of 1882 to 1885. It is thought to be caused by the previous economic excesses, leading to a subsequent price depression or deflation. Before the days of Keynesian gospel, there was no plan of governmental intervention while 1 million workers, approximately 1 in 5 Americans, was out of work. As it turned out, the ups and downs are just parts of the nature of the U.S. economy, which in the bigger picture, enjoyed a great expansion for almost half a century, from the mid-1880s into the early 20th century, making it the most representative episode of the Gilded Age. Like clockwork, the Gilded Age was punctuated with short bouts of panics and minor recessions or depressions. They were inevitable structural boom and bust defects of the unregulated finance and economy of that epoch. Just like the famed legends of lawlessness and gunfights that are iconic to the American Wild West. Financial panics and short bouts of depression are the chronic pathological conditions of the lawless, unregulated financial and industrial practices of the American economic centers in the East. Unlike political governance, whose stability owes to the constitutional system founded on the insightful and foresighted political philosophy of the Age of Enlightenment, the governance of the economy has been a learning experience of growing pain, because the economy of modern industrial revolutions has always been unprecedented in the human history, always in uncharted water to this day. And thus, economy governance is a series of inventions of the barn door after the horses have bolted. The biggest barn door, and the greatest American financial invention offered to the world, was the establishment of the Federal Reserve in 1913, whose power reigns supreme to this day. When the Fed sneezes, Wall Street catches a cold. Unlike the Constitution Republic political philosophy, the Old World had no lessons to offer, as the U.S. economy in the Roaring Twenties was already eclipsing that of the established European powers, and the American century was well on the way. Notwithstanding with occasional hiccups, this great growth episode was enabled by transformative innovations. From the method of mass production, to the scientific and technological progress, the episode marked the beginning of the second industrial revolution, brought by the electricity. Innovations such as long-distance telephone network, wireless communication, the wireless music box or radio, were no less disruptive, transformative, and revolutionary in its days, than today's computers and the Internet. What mentioned earlier about episodic recessions in the 19th and early 20th centuries is not idle talk, it can be examined numerically. Consider the situation before and after the 1929 Great Depression. Fourier analysis gives the power spectral density, on the log-log scale. To see the details, we can look at them on the linear scale. For part 1 on the left, there is a dominant peak at 3.4-year period. The Fourier component of this peak can be superimposed on the chart. There is a rough coincidence of the recessions and the cycle peaks, suggesting that indeed, recessions tend to occur roughly every 3.4 years for part 1, before 1929. On the right-hand side, there is no dominant peak, but 2 or 3 peaks together. This means that there isn't a clear cycle. The 2 highest peaks correspond to an 8.5-year cycle, and a 5.5-year cycles. Neither cycle has many coincidences with the recessions like the part on the left. An interpretation is that after the 1929 Great Depression, there was a great lesson learned in the governance of the economy, that helps reducing the wild and frequent economic crises of the past, for a more stable economy. The Great Depression from 1929 to 1933 was the second longest recession, along with the largest swing of the stock market in the U.S. history. The episode images of the downtrodden, the unemployeds, the breadlines, became the iconic representatives of the human toll of an economic crisis. One of its legacy was the Keynesian intervention by the government, leading to today's panacea of stimulus money and quantitative easing. The inflation of 2022, the highest in 40 years, is likely due to the largest single-dose increase of monetary supply in 2020, in order to avert the COVID-19 recession. The NBER's Business Cycle Dating Committee maintains a chronology of U.S. business cycles, etc., etc. The NBER's definition emphasizes that a recession involves a significant decline in economic activity, etc., etc. Because a recession must influence, etc., etc., the committee, etc. The committee makes a separate determination, etc., etc. In the 5 paragraphs above, the definition of recession is
black and white, clear as crystal.
However, while the explanation is enlightening and elucidating, it is difficult to know what data the committee considers, and how to create a mathematical algorithm based on the committee's judication, that can classify an economic episode as an expansion or a recession. This presentation approaches the topic of recession, not from the academic economics perspective, but from the empirical data analysis perspective, the data being the quantities or metrics, most relevant to the general public interest, such as unemployment. In this perspective, the question, what is a recession, can be paraphrased, what does recession mean to the common people, such as job, income, mortgage, or rent payments? Consider this chart of the unemployment rate in the U.S. from 1948 to 2022. The most remarkable feature is the episodic occurrence of a sharp rising edge, like a wave of layoffs, and a slow gradual recovery. The recession episodes, as determined by NBER, are overlaid as the vertical yellow bars. This is a very well-known and popular chart, showing the consistency of a rapid rise of unemployment being associated with a recession. As mentioned, this is perhaps the single most important issue to the public. Those with a job may be oblivious to a mild recession. But those who lose jobs, or small businesses have sharply lower revenues or face bankruptcy, such as from mom and pop operations, to small companies, have to bear the brunt, the stress, and the misery of an economic downturn. Along with unemployment, GDP is the other most indicative metrics of the economy. The top chart shows the US GDP from 1947 to 2020, and the bottom is its episode-to-episode change. The recession episodes are overlaid as the vertical bars. It is clear that every episode of negative change, that is, a decline of GDP as marked by the red arrows, is by definition a recession. In addition, there are episodes, as marked by the yellow arrows, where the GDP growth was not negative, it merely stopped growing or slowed down. Yet, these are also recessions with the associated unemployment. Recessions can be viewed from two perspectives. One is the macroeconomic perspective of the NBER. This involves digesting economic data, applying expert knowledge, and making a judgment call, a binary classification, recession or not recession. This perspective is essential to the policy makers for the sake of economy governance. Should the country have quantitative easing or not, is a binary, yes or no decision, involving both the executive and legislative branches. It is understandable why, what's in a name, can be politically charged. Another perspective is data-centric, focusing on its effects. Recession is not a binary yes or no decision, but merely a descriptive terminology, used to collectively characterize the various economic conditions of public concerns. Unemployment, business downturn, loan default, or bankruptcy, stock markets, etc. This presentation is an exercise of data calculations based on the second perspective. The two perspectives are not different, they are two sides of the same coin. Consider the NBER process. It is a classification based on human expert knowledge. A fun textbook exercise here is a sort of, quote-unquote, reverse engineering the NBER process. The data available are unemployment, GDP, and other to be discussed later. The data will be associated with the NBER classification results, which, altogether, forms a training set. The training set is fed to classification algorithms, which yield classifiers. Shown are the various nominal classifier types. A further secondary committee type classification can be done based on the collective results of all the classifiers. While for governance, recession is a binary status, or Boolean, GDP and unemployment are quantities of continuum values. It's not enough to say GDP or unemployment is up or down, but it matters how much up, how much down. In the follow, we will examine the continuum analog relationship of GDP and employment, not their Boolean up or down correlation. Hence, this will involve a bit of algebra. Besides the unemployment rate, a related quantity useful for calculation is the employment level, which is the number of people who work. There were 58 million workers in 1948 and 158 million in 2022. The relationship of the two quantities can be seen by superimposing the recession episodes. As evidenced, a rise in the unemployment rate in a recession corresponds to a dip of the employment level, and vice versa. The objective here is to run a regression calculation on the relationship of the gross domestic product and the employment level. At a given time tk. We assume a very simplistic concept, the GDP is equal to the number of workers, multiplied by the mean productivity per worker of the episode. Productivity, on its own, is a very complicated entity depending on many variables. Here, in this highly simplistic model, it is just an empirical quantity, P of Tk, defined by the formula. The concept of effective mean productivity can be illustrated with a chart. Take the gross domestic product, divided with the number of workers, yields the productivity of each worker in thousands of dollars per individual per quarter. This also shows a fundamental canon in economics. That the wealth of an economy is gained, not by a population and workforce increase, but by the increase of worker productivity. In the last 3 centuries, this worldwide productivity has steadily increased exponentially, thanks to innovations, and scientific and technological advances. In the last 70 years, this productivity in the US has increased 2.6 times in real dollar, an increase of approximately 1.3% annually. The rationale of the regression is the follow. Shown here are the zoomed-in linear charts of the GDP and the employment level. In mid-2008, because of the financial crisis, there was a big dip of employment and a corresponding decrease of the GDP. In early 2020, there was an even sharper dip in employment and GDP because of COVID-19 pandemic. While both GDP and employment showed large variation, the productivity has been steady and not susceptible to the ups and downs. If there are more or less workers over a short period, their contribution to the GDP will change proportionately, but the worker productivity should not deviate from its gradual and steady trajectory. There is perhaps an exception for the COVID-19 pandemic, in which the slight dip in productivity might have been affected by practices such as remote working, travel restrictions, and other measures intended to contain the spread of the disease. In any case, the quantities to be correlated are not the GDP and the employment level themselves, but the relative changes of these quantities. After some algebra which can be found in the appendix, the relationship, to the first order, is a simple proportional relationship that regression calculation can be applied. Coefficient ρ k is simply the ratio of the productivity k plus 1 to k, which should be close to 1, as the productivity changes very slowly from one episode to the next. The relation can be expressed with a simple form, y is equal to ax plus b. Both a and b are variables. A further simplifying assumption is made, that a and b fluctuations are small, and can be treated as roughly constant. A lot of algebraic reduction was made in order to make all the quantities unitless, which helps avoiding the messy problem of orders of magnitude mismatches. The GDP and employment data are then computed to yield the fractional change variables. Random fluctuations of these quantities are essential to test this hypothesis. If the fractional change of the GDP or the employment level were constant, the variable would have only one value, and the linear hypothesis y is equal to ax plus b could not be tested. In this vein, the large data spikes associated with the recessions are crucial to this statistical analysis. At each time point, the unemployment data contributes x, and the GDP data contributes y, together for an xy point of a data set. Descriptive statistics including the mean and the 3-time covariance ellipsoid are shown. Linear model fit, represented by the straight line, shows that indeed, there is a strong positive correlation between the workforce and the GDP as hypothesized. But the fitted model parameters, a hat and b hat, are important. The yellow ellipsoid represents the 95% confidence region of the parameter estimates. The value of b hat, 0.013, is roughly consistent with the model. However, a hat is substantially smaller than the expected value of 1. There are other unaccounted variables and factors that cause the data so widely scattered, affecting the estimate of parameter a. An approach to reduce this problem is to use data smoothing techniques. Data smoothing gives the advantage of reducing unwanted random quantities, at the cost of losing relevant information of important quantities, as this can be seen in the shrinking scatter distribution on the left. There is an optimal range of smoothing, and a criterion is that the confidence ellipsoid, relative to the estimates, is smallest, or if one of the parameter has another independent estimate, select the smoothing that gives the closest value to that known estimate. In this case, that parameter is b, and its independent estimate is given by this formula, which gives 0.0119. It is remarkably fortuitous that the smoothing that matches this case yields a hat 1.01, which is exactly as expected. The data is quarterly, the optimal smoothing time window is 1 year. One might wonder if the 1-year window smoothing perfectly cancels out the well-known annual seasonal effect. Given this result, it can be said that indeed, for every plus or minus 1% change of the workforce, there will be an expected corresponding plus or minus 1% change in GDP. The answer is a yes. Earlier, two most recent recessions were considered. The 2008 financial crisis, there is a statistically significant bump in productivity. Then for the COVID-19 recession, there is a noticeable dip. This is more than anecdotal. This graph shows productivity versus time. There is almost always a positive slope associated with the rise of unemployment in a recession. A detailed rigorous statistics analysis will be in another video. The key point is that productivity is unlikely to be a completely independent random variable with respect to GDP and employment for the recession episodes. During a downturn, the least profitable businesses are often cut. Workers may lose jobs not by any fault on their own, but simply because of the misfortune of being in a wrong business at the wrong time. Things change. With the elimination of low productivity business units, the mean productivity of the remaining ones rises. This may explain why in some recessions with high unemployment rate, the GDP slowed down but did not quite go negative like what the linear regression result would suggest. The following is a conceptual illustration of approaches to classify recession. Classification can be as complex as how the data are used. Here, a very simple, if not the most simplistic approach is presented, because it is transparent and useful to illustrate the basic idea. Step 1 is to create a training data set. Consider the unemployment data. The first part of the training data set is to extract the data associated with recessions. The naive approach here uses only 2 data points for each recession, the 2 endpoints, shown as the 2 colored points on the graph. A green point is at the start of a recession, the magenta point marks the end. Consider a specific recession, the 2008 financial crisis. Let x1 be the start point and x2 be the end point. Then, we create 2 new variables, variable 1 and variable 2 as shown. Variable 1 is the net job loss. Variable 2 is how fast the jobs are lost. The rationale is that these 2 properties, based on initial gut feeling, appear to be the most typical for all recessions. Then the new variables form a data point, which can be plotted, shown as the red dot on the graph. Each recession is associated with 1 data point. Collection of all the recession data points, shown as red points, form one part of the training set. Technically, all episodes outside the recessions are non-recession. However, we don't use an entire episode between 2 recessions, but only a random sample within a non-recession episodes. The reason is there is a large statistical difference between the recession duration and the no-recession duration. We wish to avoid giving an algorithm the bias that anything long is unlikely a recession, and anything short is likely a recession. Hence, we use the same statistical characteristic of the recession duration, which can be modeled as a log normal distribution, to generate random episodes within the non-recession windows for training data. Shown here is an example of such random episodes, marked by white vertical lines and points. Each random non-recession period is associated with 1 green data point. There are a large number of combinations for random training set. Shown here is an example of many sets. The sets can be cumulative as shown. There are over 600 distinctive non-recession episodes in this example, 50 times more than the recession episodes. This is only for concept illustration, only a small fraction of it is sufficient for the training set. The training data set is fed into the classification algorithm, and the output classifiers can be evaluated. Given the obvious training data pattern, the result is no surprise. All classifiers yield textbook 100% accuracy. All confusion matrices are perfect. The 64 cases of no recessions are correctly classified as such, and so are the 12 recession cases. There is zero confusion, that is, no recession case is mistakenly classified as non-recession and vice versa. Although only 6 common classifiers are used, including the most simplistic ones, it is of little doubt that other classifiers would work just as well because the data are so clear-cut. It is useful to view the probability calculation to evaluate a classifier. Shown here is the probability distribution of neural network classifier. The columns represent the training data points. Red columns are associated with recessions, and green columns are associated with randomly generated non-recession episodes discussed earlier. The cyan surface is the probability for non-recession as a function of variables 1 and 2, and the orange surface represents the probability of recession. As expected, all the green columns fall into the region where the probability of no recession is practically 1. Likewise, all the red columns fall into the region where the probability for recession is 1. What this means is that this classifier is practically perfect in determining whether an episode is a recession or not. The shape of the probability surface is the characteristic of a classifier. As expected, logistic regression, nearest neighbors, naive Bayes, decision tree have simple probability distributions, reflected their simplistic algorithms. Support vector machine and neural network are more complex and computationally intensive. In summary, an analogy is this. A group of people are assigned the task of looking at the data and studying the results of the NBER. Then, they come up with their own rules, represented by the probability functions illustrated previously. All 6 classifiers are perfect, as the rules correctly replicate the NBER results and randomly generated examples. In other words, the classifiers have learned to imitate the NBER approach. A few extra notes on this problem. It was found that including both GDP and unemployment data yielded a more robust result. A couple large recessions were split up, with one half used for training, the other for validation test, and the classifiers were perfect. However, the data were minimally processed and the computation was more intensive. Second, the unemployment data could be used either as is, or its time derivative. The time derivative data are convenient and advantageous for certain data processing. In fact, variable 2 in the previous discussion is the time derivative, which provides another discriminant dimension. The idea of using this variable actually came from the more complex classification approaches that used the time derivative data. Lastly, the GDP data might not have as much predictive value as the employment, likely because it is after the fact. People lose jobs first, then GDP declines afterward. On the other hand, it can be seen that when the unemployment rate ticked up, at a certain job loss speed, it became predictive the following deluge, hence it can serve as a warning of a recession. The classification shown above is the most naive, simplistic, and chosen precisely for that reason. It uses the minimal of 2 scalar variables, which is convenient for visual presentation with 2D and 3D plots. Classifications that use heftier data are more opaque, not conducive to graphical presentation, and are mysterious even to an author. But they may produce more insightful results, such as this example. Why these 2 episodes, next to recessions, are not considered recessions. Why this episode is not a recession. The unemployment rate increased as much as other recessions. A speculation is that the GDP at this quarter recovered from the dip, hence, NBER might have decided that the recession was over. However, some classifiers gave a different result. The classifiers think that the recession is wider, represented by the white vertical bar. They did this by a random walk search for recession. A classifier starts out by selecting a random time point. Then it adds a base episode to the left or right, while calculating the probability of recession. If, say, adding an episode on the left decreases the probability, then it drops the leftmost one, and adds one on the right, then calculate the probability again. It keeps on walking left or right, adding and dropping episodes, until it finds a probability that is greater than 50% chance of recession and higher than any left or right base episode, then it will declare it finds a recession. Why some classifiers give this recession episode wider than that of NBER? Let's take a look how the classifiers are trained. The classification algorithms were given the data, and told what is a recession, and what is not. The classifiers might have learned to associate a large dip of GDP in the top graph, with a spike of unemployment speed in the bottom with a recession. To make the algorithms robust, moving average smoothed out data were also given for training. Back to the discussion. Now, we may see why the classifiers did what they did. The GDP did not truly recover, because it dipped again. The smoothed out data of GDP change shows that the GDP was still below the long-term trend, on the way to recovering, but not quite there yet. Meanwhile, the job loss was still maintaining its speed. Hence, the classifiers, having learned to look at a broader trend, a V-shaped pattern of the GDP, have a rationale to call that recession episode to be as long as it is. This shows that classification algorithms, although complex and opaque, may give unexpected insights. What can give a heads up on a coming recession? As discussed with the regression calculation previously, GDP is a confirmation, not a harbinger of layoffs in a recession. It declines because there are fewer workers. A sharp rise in unemployment appears to be one of the best indicators of recession. A question is how the data perform in real time. In real time, the unemployment data are smoothed with moving average, but only with past data at any point in time, because the future is unknown. Hence there is a time lag, by the duration of the smoothing window. Next, the time derivative is calculated. Every time the unemployment rate goes up, its derivative moves into the positive range. A warning point marked where the derivative exceeds certain threshold. The duration when it is above the threshold, forms an episode of interest. All other parts of the data are neglected as irrelevant. Every warning point or cluster of points is associated with a recession. Nearly 100% reliability. The question is how timely is the warning? For long recessions such as the 2008 financial crisis, the warning is at the start of the NBER recession. It should be noted that NBER recessions are not in real time. They are retrospective, in other words, at the time the recession actually started, NBER did not know it. Only after the fact and looking back at the historical data did NBER make a chronological call on the recession. The COVID-19 recession was so sudden and fast that the 6-month moving average window cannot be sufficiently timely to catch it. For the present, there is no sign of recession coming based on the unemployment data. Job loss is a recession warning at the individual level. Residential mortgage and personal credit card are in the same category as job loss statistics. At the business level, data of lease financing and business loan delinquency are complementary to the job loss data, and can be highly valuable as corroborative warning signs of an economic downturn. Same approach as in unemployment rate can be applied. Unfortunately, the data are very limited in time to test the hypothesis, but can be used for real-time warning. Business activity surveys, such as Purchasing Managers Index, Global Manufacturing Index and similar, offered by commercial market intelligence organizations, are most often used as early warning. Every recession is associated with a major stock market dip, however, not every major stock market dip was predictive of a recession. The stock markets reflect the collective, quote-unquote wisdom of investors who pay attention to the smallest, most trifling purveyor of business and finance bad omen. Yet, the record of the stock market indicator is less than stellar, as investors can be excessively skittish. And the use of an economic predictor is to beat the market. Hence, following the herd is self-defeating. However, for machine learning, the stock market can be a contributory source of data to be used along with others. Finally, there is always the kitchen sink. Oil, copper, gold, whatnot. It is always tempting to include everything and let machine learning algorithms work all out. The ideal artificial intelligence system is to self-teach through trial and error feedback and feed forward. Ultimately, to discover the underlying mechanism that leads to economic instability, and to prescribe stabilizing feedback control like a car cruise control system.